in polar coordinates, a point is located in the polar plane by rotating a ray of length r through an angle of theta. The thing is, theta grows and r can grow and get smaller. And as it moves, it'll trace out a curve. And an ordered pair is given by r theta, where r is the hypotenuse of a right triangle with sides x and y. So there's our conversion formula to go from x and y to the r. We can also get theta because I know the tangent of theta is y divided by x, and the x coordinate is r times the cosine of theta, and y is equal to r times the sine of theta. So last time we had practice going back and forth from rectangular coordinates to polar coordinates to rectangular coordinates. But what I wanted to do is go through all of our graphs in polar form so that we can learn how to graph things quickly. And then, just as we did in 6.1, if you know the graph, then you can find the area enclosed by the graph. So we'll derive a formula that computes the area of polar curves and see if we can use it. So from last time, we said that an equation of the form r is equal to 4 is a circle centered at the origin of radius 4. I can show you that this is true simply by squaring both sides. Take that equation, square both sides, and you get r squared is equal to 16. Then use our conversion factor that r squared is x squared plus y squared, and bam, I've converted that formula to rectangular coordinates, and hopefully you recognize that now as the equation of a circle centered at the origin of radius 4. So when you see r is equal to a number, you know you've got a circle. If you see theta is equal to a number, then you have a ray, but for all directions, so you'll have a line segment through the origin. So for instance, theta is equal to 5 pi over 6. Gives a line. I go over to 5 pi over 6, which puts me about right here, and then draw that ray and make it go back this way. There's that line. I can find the equation of that line in rectangular coordinates simply by taking the tangent of both sides. Take the tangent of both sides, and I get the tangent of theta is equal to the tangent of 5 pi over 6. But the tangent of theta is y divided by x. The tangent of 5 pi over 6 is the sine of 5 pi over 6 over the cosine of 5 pi over 6. And so that reduces to y over x is equal to negative 1 over root 3. And the equation of the line then is y is equal to negative 1 over root 3x. A line through the origin of slope 1 over square root of 3, negative 1 over square root of 3. But I don't want to have to convert everything to rectangular coordinates and only to graph it. The easy graphs I will, just to convince you what they are, but then we have some other graphs whose equations in rectangular coordinates are, you wouldn't recognize what the graph is in rectangular coordinates, but you're going to recognize what the graph is in polar coordinates because I'm going to make you.
All right.
So let's complete our look at circles. This is a circle centered at the origin. If I tack on behind this number a sine or a cosine of the single angle, those are also equations of circles. R is equal to a number. R is equal to a number times the cosine of theta. R is equal to a number times the sine of theta. Those are all circles. This one's centered at the origin, these two are not. Let's figure out how to graph the ones that are not centered at the origin and convince you that they're circles. So let's sketch a graph of R is equal to 4 cosine theta. I'm going to graph it two ways. First, by plotting some values of theta in the xy plane, and then by converting this to x and y coordinates. So let's see, I'm just going to plot the values that cosine gives me nice numbers. So for theta, I want to plot 0, pi over 3, pi over 2, 2 pi over 3, and pi. If I need more, I'll have to add some. That's all I have room for right now. Zoom in a bit so folks can see that. Okay, let's just go over it. Flush. Okay, cosine of 0 is what?
4.
Cosine of 0 is 1. 1 times 4 is 4. So R here will be 4. So when you have an angle of measure 0 with the positive x-axis, the ray has a length of 4. And remember, our ray has a pencil at the end of it, so we'll plot a point right there. So let's say that this is 4, plots this point here. Now I'm going to move my ray to an angle of measure pi over 3. So 1/3 of the way around here would be about right here maybe. So I'm going to think about my ray here. I don't know how long it is just yet, but I'm going to find out. I'm going to put pi over 3 in for theta. I chose pi over 3 because the cosine of pi over 3 is a half. Half of 4 is 2. So here I have a ray of length 2. If that's length 4, then length of 2 plots a point right there. Now I have a ray coterminal with the positive y-axis. So when my angle lands my ray right here, the point that is plotted is 4 times the cosine of pi halves. Quick, what is the cosine of pi halves?
0.
And 4 times 0 is 0. So when my ray is here, it plots this point right here. Now my ray is at 2 pi thirds. So if this is 1 pi third, 2 pi thirds is somewhere, that's 1 pi third, 2 pi thirds is somewhere through here maybe. Does that look, trying to make that look like thirds. At 2 pi thirds, I take the cosine of 2 pi thirds and I get negative 1/2. So here I have 4 times negative 1/2, I get negative 2. So if I'm here, the point that's plotted is back here, negative 2. And now my ray is coterminal with the negative x-axis. Cosine of pi is negative 1. So when my ray is here, it plots a point back at negative 4. So it goes back here. Okay, so that's going to trace out the entire circle. It's going to look something like this. You're just going to have to believe me on that. That's not a bad circle right there. So maybe those 4 points weren't so convincing. Let me convert this to rectangular coordinates. Here's how I'm going to convert it to rectangular coordinates. I left a gap between the 4 and the cosine of theta. Because if I had an r in front of that cosine, then I can make a swap for x. So I'm going to take that equation and multiply both sides by r. I'll multiply by r here and an r there. Now I have conversion factors. R squared is x squared plus y squared. And r cosine theta is x. Now I'm going to move that 4x over and put it right here. And I'm going to leave you a gap because you're going to complete the square to find the center of this circle. Remember how to complete the square?
Ooh.
I have to add a number here and add that same number there.
Oh, yeah.
What number do I add so that x squared minus 4x plus that mystery number makes up factor a perfect square?
Could it be positive 4?
It is positive 4. Factors of positive 4 that add to negative 4 are minus 2 and minus 2. So this now factors as x minus 2 all squared. Just remember, if you complete the square, you can always take half of the middle term, square it, and that's the number you add, and you always add. So this left side factors as x minus 2 all squared plus y squared is equal to 4. In this form, do you recognize this as the equation of a circle in rectangular coordinates? X and y are both squared.
Yeah.
This has moved the x to the right 2 units. Y stays at 0. To the right 2 units, so this is 2, that's the center of the circle, and it has a radius of 2. So it should be nice and symmetric. X is equal to r cosine theta will always give you a circle symmetric to the x-axis, right? Cosine is even, so it should be symmetric to the x-axis. And it'll have diameter of a. One side will touch the origin, the other side will touch, in rectangular coordinates, the ordered pair A0. Where do you guess this type of circle would be?
Along the y-axis.
Along the y-axis. You could do the same thing, multiply both sides by r, complete the square, and you'll find this is a circle with a diameter of a, tangent to 0, centered on the y-axis. So these ones here will look like that. And this point in rectangular coordinates is 0, a. R is equal to a, r is equal to a cosine theta, r is equal to a sine theta are all equations of circles. Next, I want to graph something called cardioid. If I take any one of these two equations and add or subtract the number a from them, it's going to change my circle into a heart shape called a cardioid. So the general form for that, r is equal to a plus or minus a cosine theta. R is equal to a plus or minus a sine theta. So I need this number to be the same. When it's not the same, it essentially has the right shape, but it takes the little indentation and makes it a little wacky. But these are all graphs that are cardioids. You'll find cosine cardioids are going to be symmetric to the x-axis. Sine cardioids are going to be symmetric to the y-axis. All it does is it distorts those two circles a little bit. I'm going to show you a graph by plotting points. Put more here in the middle. Put more right here. So what I'm going to do is use that same one that I just did, but I'm just going to put 4 plus 4 cosine theta so that we can use those same values that we plotted. So I'm going to reproduce this table here, just add 4 to all of those numbers there. Oops, I want theta. plotting 0, pi over, I'm not even gonna plot the pi over 3s. I'm just gonna plot the coordinate, the angles that are coterminal with the coordinate axes, and we can put the pi over 3s in there later. So 0, pi halves, pi, 3 pi halves, and then whatever at 0 is the same at 2 pi. Over there, you said cosine of 0 was 1. So if I take this 4 and add the other 4 to it, I should get 8. At pi halves, we were at 0, so I add 4 to that, and I'm at 4. At pi, we're at -4. Add 4 to that, we go back to 0. So now I'm going to ask for a little assistance. Can anybody tell me the cosine of 3 pi halves? 0 still. So here I'm going to get 4 again. And then cosine of 2 pi is the same as cosine of 0, so I get 8 again. And in there it gets those little numbers in between, right? The 0s and 1s are the most that that'll be, and then it'll hit the halves and the square root of 3's over 2, blah, blah, blah. So theta is 0, puts me out here at 8. Now it's moving from here to here, tracing out a continuous bunch of points, but then it goes over to theta r is 4, so make it about half that length. And then it goes to pi, and at pi it plots a point at the pole. Then at 3 pi halves it plots something here, and then back at 2 pi it goes there. In between those, it's continuously plotting points that are going to look something like this. Symmetric to the x-axis. What do you think happens if I put a minus sign in between the two of them for -4 cosine theta? We'll keep it symmetric to the x-axis because of the behavior of the cosine. Before -4 cosine theta is going to put the cardioid that way. But if you plot the coordinate angles on the coordinate axes, then you're all good. That's what I plotted. I plotted theta is 0, gives me 8. Theta's pi halves gives me 4. Theta's pi goes to 0. Then it goes down to -4 and back to 8. So cardioids. A plus A cosine theta is going to look just like that one. Or A minus A cosine theta looks like that one. The sine function, I think the A plus, I don't know, let's see. I think one of them does this with the y-axis coming here, and then one of them does this. This little peak of the heart is always at the pole. If I make this number bigger or smaller than that number, and this a plus or a minus, then all it does is it changes how this is indented. So if I make something look like R is equal to a different number, plus or minus A cosine theta, I'd have to plot a few points, but it distorts the shape of the heart so that it's not called a cardioid anymore. It'll either flatten that little peak out or make a loop in it. And they'll be called this, I don't know how to say it, because the C has a little action going on. It has some sort of gizmo out there, and I don't know if that makes it a hard C or a soft C.
It's like lima.
It looks like a lima bean, so I'm going to call them lima beans. And so the shape is like a heart, but and like a circle, kind of like the bastard child between a cardioid and a circle. It's just going to have a little bit of a dip right there, but not enough to make it hearty, but more than circling. Or it could go really wacky and put a loop in there. And it depends on whether or not, which one's the bigger one. I never know. I just kind of fake it. But on page something, it tells you when it happens based upon sizes. Uh-oh, lost the picture again. Let's go that way. Zoom, zoom, zoom. Okay, so what I wrote down was, if I change the number out here to make it different from that one, and depending on which one's bigger, you'll get one of these. I don't know which one. Look on page 451, I think, and it'll tell you. Or I've got a handout of these graphs, and on there it tells you, and it's on Blackboard. The next one I want to draw takes these equations here and uses a multiple angle instead of a single angle. So if I put a 2 in front of the angle, or a 3, or a 10, it makes a similar picture. And we're going to call those rose curves. Rose curves. If the equation looks like R is equal to A times the cosine of some number times theta, or same version with the sine. And pretty easy to remember that if that multiplier is an odd number, then your rose is going to have that many petals. So if R is an odd number, you'll have that many petals. If R is an even number, you're going to have twice that many petals. Not R, N. So if N is odd, you're going to have N of these little petals. And they're going to be equally spaced. For example, if N is 3, and I take 360 degrees and divide it by 3, then each of the tips of those petals are going to be 120 degrees apart. If N is even, we are going to have 2 times N petals. And again, they'll all be equally spaced. So if you can find the tip of, say, the first petal, then you can fake the other ones. But I'm going to go through and by brute force, graph one by plotting points. And then from there on out, I'll never do that again. I'll just find the first petal and measure the other ones. So let's graph R is equal to 3 times the cosine of theta. I'm sorry, cosine of 3 theta, not 3 times cosine of theta. Cosine of 3 theta. 3 cosine theta is a circle. Cosine of 3 theta is a rose curve. And I'm going to plot points in such a way that after I multiply them by 3, I'm going to get one of the nice numbers to take the cosine of. I like to take the cosine of 0, pi halves, pi, 3 pi halves, 2 pi, but also of the pi thirds, because cosine of pi thirds is a half. So I'm going to choose those values for 3 theta, but when I plot them, I have to divide them by 3. So let me go around the unit circle to see how many will fit right here. So I'm going to go 0, then I want 3 theta to be pi thirds, then I want it to be pi halves, then I want it to be 2 pi thirds, then pi, now I'm in quadrant 3, so I'm at 4 pi thirds, 3 pi halves, and then 5 pi thirds, and then back to 2 pi. And we'll see how much that draws. It probably won't get me the entire thing here. But I took a lap around the unit circle with you. Did you get dizzy? Because I went kind of fast. So before I figure out theta, let's figure out r. Cosine of 0 is 1. Cosine of pi thirds is a half. Cosine of pi halves is 0. Cosine of 2 pi thirds is -1/2. Cosine of pi is -1. Cosine of 4 pi thirds is -1/2. Cosine of 3 pi halves is 0. Cosine of 5 pi thirds is +1/2. Cosine of 2 pi gets me back at 1. Thank you very much. Now, the angles that I plot are not these. The angles that I plot are theta. So I move from here to here by dividing by 3. So I'm going to take all the angles in the middle column, divide them by 3. 0 over 3 is 0. Pi thirds over 3 is pi thirds times 1/3, which is pi ninths. Then pi 6, then 2 pi ninths, then pi thirds, then 4 pi ninths, then this will get me to pi halves. I finally finished the first quadrant. And now I'm at, divide that by pi thirds, so I'm at 5 pi 6, 5 pi ninths, and then 2 pi thirds. So I haven't gone around all the way to an angle of pi. Don't know that I need it, but let's see. Oh, yeah, those are A's. Sorry about the glare. I have some notes that I have written that I can post on Blackboard. So if you do have trouble seeing, I'll be trying to follow the notes so that you can just look at the notes. Okay, so what I need to do is cut my first quadrant up. I actually cut the top half of the circle into 9 equal pieces. Okay, so let's put my circle right here. And I need 9 equal pieces. That's going to be hard. That's going to be hard for me. So let's see. How do I get 9 equal pieces out of this?
I believe in you.
You believe in me?
I believe in you.
Gosh, dang. Well, let me do the pi 6s first. So if I cut it into 6 equal pieces, so let me imagine a circle here. And I'm going to try and make 6 equal pieces. 3 of them here. Oh, I've already done look big enough. How about that for expert measuring? Bam. Those are pi 6ths. So this angle here, oh, I missed it. A lot of good it did me to measure. That's 1 pi 6. 2 pi 6 is the same as pi thirds. 3 pi 6 is the same as pi halves. This is 4 pi 6, which is the same as 2 pi thirds. And this is 5 pi 6. Oh God, that really got all bendy over there. So this one was pi 6. This is pi thirds, pi halves, 2 pi thirds, 5 pi 6, and pi. All right, so pi over 9 cuts this arc into thirds. So let's, for jollies, say that this is pi over 9. And then I'm going to need to get a 2 pi over 9. That's 1 pi over 9. There's 2 pi over 9. That's 3 pi over 9. Here's 4 pi over 9. That's 5 pi over 9. And that one is 6 pi over 9. And then I can stop there. I'll take it from there. Okay, so there's pi 9 right there for you. All right, so I'm going to plot now. So I'm going to plot in blue. At an angle of 0, my ray hits 1. So when my angle's right here, let's say it hits 1. Now it's going to move from there to an angle of measure pi over 9, add an angle of measure pi over 9 through here. Imagine the dotted line. I'm not going to put it because it gets me dizzy. I'm going to put a length of a half. So it's going to put this point. So as my ray moved from here to here, it traced out that little bit. And now it's going to go to pi 6. That's the first dotted line, and it's back to 0. So it goes like that. Okay, that's going to make this guy, after a while, because the next thing we're going to do is, I bet we go back here. Watch me. We did the pi 6. 2 pi 9ths is here, and I have to go back -1/2. So if I extend this invisible ray back here, I'm going back. So that ray is coming down through here. I'm going back to -1/2. So it goes from there to there. Then at pi thirds, I'm down at -1. So here's pi thirds, back to -1. Then it's going to come swing on back at 4 pi 9ths. That's going to come down in here. It's going to go back to 1/2. And then at 3 pi, I'm sorry, at pi, where am I? 4 pi 9ths, -1/2. And at pi halves, it goes back to 0. So that closes that leaf up. Okay, the tip of the next leaf is going to be on the 2 pi thirds. That's where it hits 1 again. So it's going to move from here. It's going to do all those goofy numbers in between there. Then it's going to come back, just trust me on this, to here. And then finally, it's going to go back to here. Now I want you to notice that the angle measure from 0 to 2 pi thirds is 120 degrees, because 2 pi thirds times 180 over pi, our conversion factor to go from radians to degrees, 2 times 60 is 120 degrees. So that means I'm not going to have any more petals. I've got 3 equally spaced petals, the tips of which are 120 degrees apart. Doesn't show it very well here. Let me retrace it with a better blue. So the tracing went like this. It's as my angle rotates counterclockwise, it goes here, here, back, and back. When I was a little girl, I had something called a spirograph. You ever heard of spirograph? It was a little toy that drew these shapes in that way. You just took your little thing and moved it around this gear. It had circles with gears, and you moved it, and it traced it out so pretty, just like that. So once you recognize that you're going to have odd number of petals, just find the tip of the first one. Cosines are easy because cosines are symmetric to the x-axis. The first petal is always going to have its tip somewhere on our old favorite x-axis. Then you can figure out where the rest of them are by taking your 360 degrees and dividing by n, unless n is even. If n is even, suppose I'm graphing cosine of 2 theta. That tells me I have 4 petals. 360 divided by 4, 90. Every 90 degrees, that cosine is going to spit out a petal. So cosine of 2 theta is going to look like a petal here, because the cosine of 0 is 0. It's going to go the same way. It's going to start here, 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 and then meet back up at the y-axis. That's the graph of the cosine of 2 theta. Cosine is always going to be 1 when theta is 0. Sine is going to be trickier, because the sine is symmetric about the y-axis, but that doesn't mean the first petal's on the y-axis. It's going to be in such a way that if you fold it about the y-axis, it shows symmetry. Okay, so let's sketch a graph of, let's do an even one. How about we do a sine of something, something. Let's just do a sine of 2 theta. Let's sketch the graph of f of theta, or r, is equal to the sine of 2 theta.
the application of these?
Well, we're gonna find the area enclosed by them, and we're gonna find the length of the arc around them. So they're gonna be our tools, our pictures to have more fun with. But now, if you think in terms of, I don't know, something in engineering, give me something in engineering. Sound waves occur in kind of circular patterns. Magnetic fields move kind of wacky. Those can be described with polar curves. That's the extent of all my knowledge. I just use them in calculus.
Sorry. I always just like to know what that thing gets applied to. That's interesting.
A lot of stuff is because it's there. And you haven't got it here, so I have to take it from there and put it there. And then you use it how you see fit. Right? How many times in your life did you use, say, the intermediate value theorem? We covered it in Cal 1. I used it a lot in my life because in my life I had to find zeros of a function and I didn't have a calculator that traced and found the zeros that way. So I had to find a function that changed sign and then just keep finding smaller intervals in which it changed sign, and I could approximate the zero to some level of accuracy. Now they have calculators that do that because somebody, programmed that into a calculator. So you've got software that can draw these pictures. Well, what fun is that? Go into Mathematica and just graph this in polar. There it goes. And the Inspire calculator can graph in polar coordinates. I now know an Inspire calculator. That's the one that most kids had in high school when you do. Did you guys have to buy an Inspire calculator? Maybe it's for the kids that are young.
I did all my high school math on like a TI scientific calculator.
Well, back in my day, calculators weren't allowed. We had to use our noggins. All right, I said I was graphing the sine of 2 theta. We're going to come up with a 4-petal rows. They should all be 90 degrees apart. If we can find the first one, then we can get the rest of them. So I need you to think, sine of what angle is 1? It'd be pi over 2. So if I'm plotting, I want to graph r is equal to 3 sine of 2 theta. I want this number here to hit pi over 2. So I'm going to put my 2 thetas there. I know sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi puts me back to 0. Sine of 3 pi over 2 gets me back to 1 again. Agree? And then sine of 2 pi is 0 again. So let me see if I can get a graph just using those as 2 theta. Now remember, I need to plot theta, so I'm going to divide by 2 to get these numbers after I compute r. Okay, so again, sine of 0, 0, 0 times 3 is 0. Sine of pi halves is 1, 1 times 3 is 3. Sine of pi is 0. Sine of 3 pi halves is -1. Times 3 gives me a -3. Sine of 2 pi is 0. Now let's get theta by dividing the middle angles by 2. So I get 0, pi over 4, pi over 2, 3 pi over 4, and pi. Let me rub that off and graph it right there so the camera can see it. All right. So I'm just looking between 0 and pi, and I've got just the fourths. Those are easy. So pi over 4 here. 3 pi over 4 is there. Ooh, it's straight. So 0, pi over 4, pi over 2, 3 pi over 4, and pi. When my angle is coterminal with the positive x-axis, I plot a point at 0. Now my angle is up here, pi over 4. I need to plot a point 3 units long. So let's say that that's a 1. 1, 2, 3. Well, how did it get from here to here? Mystery. Do you think it did wacky things, or do you think it made a pedal? Now we're at pi over 2 and we're back to 0. I just found the first pedal. It goes out and back. This made one pedal. And that's going to make a half of a pedal. At 3 pi over 4, I have to plot -3. So that was 3, there's -3. So look how it went. It goes from here to here to here, back down to there. And now it's going to close. At theta's pi, it goes back to 0. Then it's going to come down where? You think it's going to go here or here? Follow the pattern. It's going to come out here, right? And then right there. If you know it's a rose and you find the first petal, and you know it's going to have an even number of them, make them all 90 degrees apart. Measure the distance between an arc of length pi over 4 and 3 pi over 4 by subtracting. You get 2 pi over 4, which is pi halves, or 90 degrees. Those are all 90 degrees apart from tip to tip to tip. Okay? Then one more graph is, looks like the infinity symbol. If you take the double angle of a sine and cosine and set it equal to an r squared, it cuts off these negatives and just gives you the positive tips. And so r squared is equal to some number times the cosine of 2 theta is going to give you an infinity symbol on the x-axis. R squared is some number times the sine of 2 theta, just gives you this pedal and this one. It gives you a pi over 4 centered infinity symbol. Now, if A is negative, in either case, if A is negative, it does that. If A is negative, it does that. But that's for the R squared graph. That has another name other than infinity symbol. I think it's called a lemniscate. I think, because the C has another goofy thing on it. But if we know what we've got, then we can do our calculus to it. And one of the things that we want to mimic is finding area enclosed by these graphs. Now, when we're in the XY plane, we take our graphs and we make nice little rectangles out of them. When we're in the R theta plane, we're going to chop things up with rays that are delta theta units apart from each other. And we're going to make sectors. So anybody who's anybody knows how to find the area of a circle. What is the area of a circle? Pi r squared. So what about an area of a sector of a circle? I don't want the whole circle. Suppose I just take an angle, say, of measure pi over 6. There's a circle whose area is pi r squared. But I just do an angle of measure pi over 6 and have a pizza slice. How do I find the area of that pizza slice? How many sections would there be in a 2 pi radian if each of them are pi over 6 radians? 12. So if I take my angle, pi over 6, and divide it by 2 pi, it will tell me that I have 1/12 of the circle. Because the pi's will cancel. And then I have pi over 6. That gives me 1/12 of the circle. So the moral of the story is, if I know an angle of measure theta, and I want to find the area of the sector subtended by an angle of measure theta, Then I do my pi r squared, but I know that I have a theta over 2 portion of the circle. Actually, theta over 2 pi, sorry, theta over 2 pi, just like I did here. Then the pi's will cancel, and so what's left is 1/2 r squared theta is going to be the area of a sector of a circle subtended by an angle of measure theta. That's going to be important. Because instead of adding up a bunch of little rectangles, base times height, f of x times delta x, I'm going to add up the areas of a bunch of sectors. It's going to follow that general pattern. So make some sort of blob to be the graph of r is equal to f of theta. Okay, so here's the xy plane. And here's my blob. Just in general, graph of r is equal to f of theta. And suppose I want to find the area enclosed, say from theta is equal to A to theta is equal to B. So this part of the blob I want to find the area of. And it's not a pretty circle. It's one of the graphs that we've drawn, but I'm just generalizing it with a blob. And what we do in calculus when we want to find the area of a region is we cut it into itty bitty teeny tiny pieces. We're going to subdivide this sector, find the area enclosed by r is some function of theta from theta is equal to A to theta is equal to B, subdivide the region with n rays equally spaced from the origin. So I'm just going to draw a few of them, partitioning the region with rays from the origin. And there's an infinite number of them in there. That's all I need for argument's sake. Each of those rays has an angle measure of a delta theta. And I'm going to make them equally spaced so that they're all a delta theta width. Now let's just pay attention to the kth partition. The kth partition I'm going to outline in red, and I'm going to try and find the area enclosed by the kth partition. Is that somebody trying to get in? Okay, but you've got to use your imagination. These rays are infinitely close together. So they're so close together that when you look at this, it looks just like the arc of a circle. And I can make that just by putting them real close together. So that I have something that looks like this, where there's one R and there's another R. And then I can use, like we did when we partitioned with rectangles, we can use a left sum or a right sum by using whatever f of theta or f of x was for which one. So I can do it here. I can pick this one, say theta k, and plug it in here to give the length of r, or I can take the next one, theta k plus 1, and I can put it in here to give the length of r. That's not going to matter because we're going to do n of these and run n to infinity. So let's say I'm going to take the kth r. So I'm going to find the area of the kth sector. using this. 1/2, whichever R I wanted, so I wanted the kth one. So I'm going to use delta theta k here. So f of theta k times delta theta. Area of the kth sector will be given by 1/2 r of k squared, which r is just some function of theta, times delta theta. I'm going to do this from k is equal to 1 to n. So I make a Riemann sum. I'm going to have k run from 1 to n of my areas. And then once I do this to it, the magic of calculus happens and the Riemann sum turns into a definite integral, whose integrand looks like this: 1/2 f of theta squared times d theta. So once I do that, then we get our area to look like 1/2 f of theta squared times d theta. And we're going to do this from theta is equal to A to theta is equal to B. So whatever generates the curve goes here. Then we square it, multiply by 1/2, which we can factor out and put it on in the end, and integrate as a function of theta. And that gives us the area enclosed by a polar curve. So it's more than taking the f of theta d theta, 1/2 f of theta squared d theta, because we're cutting things up into sectors. Okay, so if you can remember this, that's an easy formula to remember. But think about what our functions look like.
Sine squared theta.
Sine squareds and cosine squareds are going to be in here. We've got to learn how to integrate sine squareds and cosine squareds. So what we're going to do to convince you first that this formula works, we're going to go back to our original example of the circle r is equal to 2 cosine theta. That was a circle of diameter 2. We can find its area based upon the fact that we know it's a circle of diameter 2. Pi times 1 squared. That has an area of pi. Now we're going to do the integral, and we're going to get the same area of pi, so that you'll believe the formula works. Because I know I have some non-believers in here, but I will make you believe that formula. I will make you feel that formula.
It's a world form.
And then send me some money. Okay. So here's our example. Find the area enclosed by r is equal to 2 times the cosine of theta. R is equal to 2 times the cosine of theta is what's under that blur. Which was this circle over here. Diameter 2. And so by geometry, we know that that radius would be 1, so area is pi 1 squared. We have pi square units of area enclosed by that particular circle. Now, let's use our brand new, never been used formula. Now use the fact that area is 1/2 the integral f of theta squared d theta. Our f of theta is this, 2 cosine theta. Here we go. Now look at the circle. It's sitting over there. It gets traced out more than once if I go from 0 to 2 pi. If you remember how we plotted it, we got that from 0 to pi. But if you just look at the picture, if I take a ray from here and rotate it to here, I've traced out the entire circle, right? Just visually. I know when I plotted it before, I got it by tracing out this ray, because these values plotted back here. So if I wanted to, I can find the area by integrating from 0 to pi, but I'm going to use the picture and say I'm going to integrate from negative pi halves to positive pi halves. You always have to integrate from smaller angle to larger angle. So I can't integrate from 3 pi halves to pi halves. I won't get that. From 3 pi halves to pi halves gives you this. Ain't nothing over there. Okay, so I'm going to integrate from negative pi over 2 over to positive pi over 2. Always integrate in the clockwise or counterclockwise manner. Okay, so now let's square it. I got to square that 2 and I'm going to get a 4. I'm going to take the 4 times the half and I'm going to get 2. Now I have a cosine squared right here. Now I'm going to be somewhat lazy, somewhat clever. I like having 0 as a lower limit. Can I use the symmetry of the circle and say integrate from 0 to pi halves and double it? That way, when I'm evaluating my trig functions, I can evaluate at 0 instead of negative pi halves. So I'm going to use symmetry, and I'm going to put a 0 here, and I'm going to double it. So I'm going to integrate 4, 0 to pi halves, cosine squared of theta, d theta. Because I'm the kind of person who likes my life to be easier than it has to be. I can relax and recline while I'm doing something. By gosh, I'm going to do it. So that's my relaxing and reclining. Now we've got the problem. How do you integrate cosine squared?
You have to use identities.
You have to use an identity. I know my identities. I taught trig last semester. I was in charge of knowing my identities. The identity that we're going to use comes from let's see if I can remember it. It comes from this. Cosine of any angle divided by 2 looks like the square root of 1 plus the cosine of the single angle divided by 2. And leave a gap here. The sine of any angle divided by 2 looks just like that, but it has a minus between the 1 and the cosine. I mean, it looks just like that. That's going to make our integration formulas nice. Now I'm going to replace each a over 2 with oh, do I want that? Yes. I'm going to replace each a over 2 with theta. So that a itself is 2 theta. So this says cosine of theta looks like 1 plus the cosine of 2 theta over 2 under the square root sign. I don't want cosine of theta, I want cosine squared of theta. So I'm going to square both sides. So here I go, I'm going to square this side, and I'm going to square that side. I'm going to replace cosine squared with 1 plus cosine 2 theta over 2. And when needed, when I'm ever integrating a sine squared of theta, I'm going to use sine squared of theta, doing the same steps, to be 1 minus the cosine of 2 theta over 2. So to integrate this, I just integrate that. That's a first degree trig function. To integrate this, I just integrate that. So here we are, back to here. These are the trig identities that we're using. Where I have the cosine squared of theta as my integrand, I'm going to replace it with 1 plus cosine 2 theta over 2. Now, I'm not going to pull this 2 out. What I'm going to do is derive the formula for the integral of cosine squared so that you don't have to remember the identity, you just remember the integration formula for the cosine squared. So I'm going to keep this all in here and keep the 4 out of the way. But I'm going to break this up into 2 terms. I'm going to break it up into 1/2 plus 1/2 cosine 2 theta. So don't worry about that 4 just yet. I'll put it on in a minute. But I'm going to look at that as the 1/2 plus 1/2 cosine 2 theta. So that's going to be my formula for the integral of the cosine squared of theta, d theta. This is a step we'll skip from here on out. Now we're going to integrate it. When you integrate 1/2 with respect to theta, you get 1/2 theta. When you integrate cosine of twice an angle, do a u du substitution. You take u to be 2 theta, du then is 2 times d theta, so d theta is 1/2 of du. So I'm going to get another factor of 1/2 when I integrate the cosine of 2 theta. Join it with that 1/2 and I'm going to get 1/4. Now what's the integral of cosine of 2 theta?
Be sine of 2 theta.
Sine of 2 theta.
Since we already have that.
And so here's my formula. I'm going to write it like this. It's theta over 2 plus the sine of 2 theta over 4. And when you're integrating a sine squared, you're doing the same calculation. The only difference is you got a minus in front of the cosine. You're still integrating a cosine when you integrate a sine squared. So the formula for the integral of the sine squared is going to look almost identical to that. The formula for the integral of the sine squared of theta, d theta, just has a minus sign here. So that minus sign's right here. So it's going to be theta over 2 minus the sine of 2 theta over 4. If you can remember these 2 formulas, then you can skip the identity step. Just add that to the list of formulas to know. You're going to use this so many times eventually, you'll know it without too much effort. So those are 2 new integration formulas. Now we got to be a finisher. We have 5 minutes to get pi radians out of this. So here we go. Integrate this, and I get 4 times theta over 2 plus the sine of 2 theta over 4 to be evaluated from 0 to pi halves. I'm going to do the trig function first. I have to put pi halves here and multiply it by 2. And I get pi. What's the sign of pi? Sign of pi is 0. Put a 0 in there. Multiply by 2, I get 0. Guess what the sign of 0 is? 0. So this term is going to provide nothing. So I get 4 times pi over 2 over 2. Put a 0 in there and I get 0. Pi over 2 over 2 is pi over 4. And I get pi. Good. So we've got to know the graphs to help us decide where the bounds of integration are. For instance, if I had this as my circle, let's make our R is equal to, say, 6 sine theta. So then this number is 6 right here. The diameter is 6. Then when I go to find the area using calculus, I have a 1/2 integral f of theta squared d theta. So I would have a 1/2 integral, put that in there, and get 36 sine squared theta d theta. And look at the picture and tell me what angles generate that picture. There's a hint, that's theta 0. That's pi halves. That's pi. Whole picture's done. I can integrate from 0 to pi. And I can do this in 2 minutes or less. You don't have to write this step down. Tell me using geometry, what is the area of a circle of diameter 6?
36 pi.
Diameter 6. So radius is 3. 9 pi. We're going to get 9 pi. Watch me. 36 divided by 2 is 18. Integral of sine squared is theta over 2 minus the sine of 2 theta over 4 from 0 to pi. Sine of 2 pi is 0. Sine of 0 is 0. Gone. Put a pi here, put a 0 there. I get 18 times pi halves. 9 pi. Okay.
That's speed math.
You too can do this in your dorm. Get somebody who had Cal 2 last semester and show them what you learned today. Just be like the dog. I'll give you a biscuit. Okay, we'll look at the other graphs and do the areas, but then we're going to find arc length. If you were to walk around a rectangular curve or a polar curve, how do you find how long that walk is? What did you miss? Did you miss that? Those are the formulas, right? Those are the formulas for the sine squared of theta, cosine squared of theta. Then we integrate them. The big thing I get is the degrees. I'm sorry about this. Again, I'll try to put my notes online and then you can kind of look at
I see the coordinates, the thing nicer.
Yeah, that's right. Okay, anybody at home have questions? Maybe now you can see it. One of these days they'll fix the camera in the classroom and we'll have a nice centered camera and I don't have to worry about getting cut off by glare and crooked angles, so hopefully. What's underneath the circles underlined? Dawn, don't know. Anybody? From the audience, want to ask anything? Hey, I'm better off then.